In this final lab, you will be using your final project data sets to investigate a relationship between two numeric variables. And to illustrate the process in this video, I will be using our opening week survey data set and looking at a relationship between risk score and fastest speed. Now, the first step in an analysis of two numeric variables is just to draw a simple scatter plot where you choose one variable as your explanatory variable to plot on the x-axis and the second as a response variable to plot on the y-axis. I'm going to choose risk score as my explanatory variable and fastest speed as my response variable. We can see, looking at this plot, that there is not a strong positive correlation, but there might be a slight positive trend. We also see that there are some unusual observations here. Namely, there's all these dots down here where students have never driven before, and there's also a few outliers on the upper end of the distribution where students have driven much faster than a typical student has driven. So these are potential problems in our regression. But let's start out just by fitting a regression model, ignoring that issue. And the command for fitting a regression model in R is lm for linear model. The syntax is similar to the t.test function we discussed last week, where you take one variable, your explanatory variable, and fit it as a function of your explanatory variable using the dataset students 15. Okay. Now, if you want to see a little bit more information about this fit, there are several things you can do. First of all, you can look at the actual coefficients using $$ coefficients. So this tells us that our linear model fit a y-intercept of about 23.9 and gave us a slope of about 2.04 for risk score, meaning that for every 1 point increase in risk score, on average, fastest speed is expected to go up by about 2 miles per hour. Okay. Now, to see if this positive slope is significant, we can use the summary function, which gives us a lot of information. The important thing for the question that I just asked is to look down here where we're given the coefficient for risk score and given a p-value for a test of significance, basically here. And seeing that this p-value is extremely small, that means that this coefficient right here is significantly non-zero, right? Meaning there is a significantly positive correlation between the two variables. You can also get the r squared, which we discussed in class, off of this output as well. Now, to investigate the effect of some of these outliers, for example, these values down here or these values up here, right, we can make a residual plot in which we plot the x values versus the residuals from the fitted model and see if there are any strange patterns or any outliers. So to do that, we go back and we once again put risk score on the x-axis. But now I'm going to put $$ residuals, meaning the residuals from the linear model, on the y-axis. When you do this, you see that the residuals are sort of randomly distributed. There are no patterns where they sort of go up and down and up or vice versa. There's also roughly equal variance, except for the presence of all of these strange, outlier variables, which most likely correspond to the outliers in our original data set. So to remove these, we first need to figure out where they are located in our data set. And if we'd like to do that, you can use the identify command, which allows you to click on points on a plot and have RStudio tell you where those points are located in your data set. Now, the syntax for doing this is similar to plot. We change plot to identify. And if you want to store the values, you can say x equals or choose your favorite variable name. The only argument we're going to add is what we want RStudio to report back to us about the observations we click on. What we're going to have it do is give us back the row names in the students 15 data set, which correspond to the strange observations. So now I can go over to my plot and I can click on the outliers, these, and then all of these values down here. And then if I click on finish, I now have, well, it labels them in the plot as well, but I now have a vector x of values in my data set which correspond to these strange observations. And if I want to actually look at the fastest speeds of those people, to see what's going on, I can simply ask RStudio to give me these row numbers of this variable. And we can see that sure enough, pretty much all those unusual observations I checked on were either zeros or they were extremely high miles per hour in this 110 here. So what we can do is we could go back and we can refit a linear model and exclude these specific row numbers, or we can more specifically exclude all the zeros and all the values over, say, 150 in our original data set. This can be done using the subset command. And the syntax for subset is subset dataset comma conditions. And the conditions that we're going to use are that the fastest speed, students 15, $ fastest dot speed. I want it to be both greater than 0 and I want it to be less than 150. So to save time, I'm just going to cut and paste this here and change this to less than, well, we'll say 160 since that was the lowest one in that set here. All right. And now if I summarize this output, I can see that it did change the intercepts and coefficients for my models quite greatly, actually. There's still a significant positive slope, but perhaps this may be in some ways a better model for actually describing the relationship between risk score and fastest speed for students who have driven, because we don't really know these observations up here. They could have been made up, and we may not want to include those in fitting a model.